Hello and welcome. In this video, I'll be covering quicksort, which is another n log n time complexity algorithm like merge sort. But it's slightly different than merge sort because it doesn't use any temporary space to merge the arrays. Rather, it sorts the elements in place in the same array. Important note over here, quicksort in itself is a family of algorithms where there are variations and variants. You can implement quicksort in more than one way. Although the basic concept remains same, that you are trying to put one element at a time in its sorted position. A sorted position for an element is defined by having all the elements before this element as a smaller element and all the elements behind it of greater value. This is when you are sorting in the ascending order and vice versa for the descending order. We call this element a pivot element whose position we are trying to sort, okay, and we are trying to put this pivot element in the sorted position within the array. Let me explain the algorithms working with an example. Let's take the example of similar example of putting people in the sequence of their heights in a queue. To do that, this time let's take two coordinators, and it is like a basic or a common implementation where we choose the pivot as the last person. Although there are different variations, as I told, you can choose anybody at random as a pivot. Okay, let's just focus on the basic implementation and one style of implementation of quicksort. Here I choose this element as or this person as my pivot. There are two coordinators, the left pointer or right pointer, and both of them want to segregate uh, people of lesser height and people of greater height at one side. Okay. In this style of implementation, we will face a peculiar case where we are not able to sort or we are not able to put the person in its sorted position in one pass. Okay. Let's begin. For this person, the happy case is finding people of greater height, and if it does, it moves ahead. Yes, this person is of greater height, yes, this person is of greater height, and this person is not of greater height, so it stops here. Now it's the turn of our left pointer to move. The happy case for this person is to find person of smaller height than pivot. Yes, this person is of smaller height, moves, yes, smaller height, and then moves again. They both are at same location. This is our terminal condition, and we stop here. And now there is no more need of moving forward. Rather, we call this as our partition point. Then in this partition point, what we are going to say is that now I'm going to partition my array or my queue in two different halves, and then I will work on them individually until unless I can't further partition. So this is again the characteristic of any divide and conquer solutions. And now let's work on the individual parts of the array to sort them. Now we take our coordinators to their respective positions and we start again. Okay, this person is of greater height. Yes, I move ahead, and this is a terminal condition. Then I just stop over here and I see that okay, yes, this person is of greater height than pivot element, and then I just swap them. Okay, now if I see this person is in the sorted position, okay, at this moment the array, like for this person its position is sorted, we are not worrying about anyone else. If you just look at this person, yes, it was the smallest person and it is in the beginning of the queue, so it is sorted for this person. Now if we again partition the array, we have only one person And if we have only one person, then it is sorted in itself. And then we have two more people. Okay, we take our coordinators in the same way, and this time our both the coordinators will be at the same position, and we again verify whether wherever we are standing, is this person is of greater height than our pivot element. Yes, then we just swap. Okay, we swapped. And now if we partition again, then again there are like only one element, so they are in the sorted position already. We cannot partition it any further. And now if you look, these three person or this portion of the queue is now already sorted. Now we want to work on the other part of the array. It works in the same way. You have your left pointer and right pointer. This is the left pointer and this is our right pointer, and this is our pivot element. So happy case for this right pointer is to move ahead only when there is a person of greater height. Yes, and as soon as it reaches the location of left pointer, it stops. Then we do a verification whether wherever we are standing, is that person is of greater height or not. Yes, then we just swap. Okay. So if we see again only this portion of array, then we have placed this pivot person whom we selected in its sorted position. Everybody behind him is of greater height. Now we partition, and in the partition what do we get? We get one person and then remaining two. So one person is already in the sorted order. We can't do much about it. And for two people, we have this left pointer, right pointer pointing to the same location. We do a similar sort of check whether whatever we chose as a pivot and wherever left pointer and right pointer are at this moment, is that value greater or smaller? Yes, greater, then we just swap it. Now if you see, these three are also in the sorted position, and the other half of the array is also in the sorted position. So in and all, everybody in the array is now in the sorted position. So this is one style and one implementation of quicksort where we have taken left pointer and right pointer at two different ends of the array. There is one more style and one more type of variation where we can implement by having both the pointers towards one side, and then we can move forward and keep a track of where did we saw the last smaller element. Okay, so let's do that exercise also. In this example, again we have same people standing in any order, and now again I choose the last person as my pivot. Okay, here what, instead of left pointer and right pointer, I have done is I have one person standing as, like, let's say standby for now. Okay, and there is main person who's going to pass through the entire queue until it reaches the pivot element. Okay, now the happy case or unhappy case is nothing. This person has been given a task, but based on whether it finds a person of greater height or smaller height, it does something differently. Okay, now as soon as it finds somebody of smaller height, it tells this person, okay, uh, take a note, like this is where I saw a person of uh, smaller height, and I'm supposed to be doing something after that. Okay, now we'll see what is that something that this person will do after updating the location of uh, last small person. Okay, last person who's of smaller value or height that this guy has seen. At this moment, it has observed first person itself is of smaller height. Okay, now assuming that this standby person keeps a note of somebody who's of smaller height and at what location we saw that person last. Okay, last visited smallest height person or smaller height person. So to begin with, let's consider -1, which is our like um, invalid index for array. Okay, so it does not know anything about where did it saw the last smallest smaller person than pivot index as of now. Now as soon as this guy see somebody who's of smaller height, it wants to swap this smaller person with somebody who's of taller height. Okay, what we want to do is we want to push all the people who are of greater height than this person towards one end of the array. Okay, and whoever is smaller, we'll just swap with the person who is of greater height. Okay, now let's say this person starts over here and tells that okay, -1, nobody, uh, nothing known so far. When we visit this first person, this is of smaller height, and what do? We say that okay, you tell me whatever you know about. I will just add 1 to it, and I will swap this person's position with that index whatever you know about +1. Okay, so what it does is it gives -1 and we do +1 to it, and what do we get? We get 0. Okay, which is also the current index of this person. So technically we don't want to swap, or even if we swap, we won't get anything. Okay, at this moment, or like this guy also updates its value to 0. This is where I saw the last visited small height person. Okay, now this guy moves ahead. Now it sees somebody who's of greater height. Okay, fine, I don't do anything, I just move ahead. And now what? Okay, I saw somebody of smaller height. What do I do now? Okay, let me ask that person, where did the last small height person was seen? Okay, this guy tells, okay, it was seen at 0. Okay, fine. Let me just add 1 to it in that case, and let me find who's at index 1. This guy is at index 1. Now wherever I am, I just swap this person with one greater value of last smaller index small value seen. Okay, so now there is a greater value over here, and we update this value back again as 1, because this is where the small height person was seen last time. Okay, so wherever you see the small height person last time, just ahead of that there should be a greater height person. That's what the idea is. Now this guy walks ahead in the queue. Everybody is of greater height, keeps on moving until unless it finds somebody who's of smaller height. Now what do? We do the same thing. We ask this person, where did you see the somebody who was of less height than the pivot index or the pivot person? It says I saw somebody of smaller height at position 1. Okay, then I will just add 1 to it, which automatically would mean that there is somebody of greater height, which is this person at index 2. Now we swap these two people. Okay, and now yes, somebody is of greater height. I move ahead and I come over here. As soon as I reach the end of the queue, which is my pivot index also, and in that case I don't do any further comparisons. I just do one thing. Wherever this last value was, okay, like wherever we saw the last small person, where we saw the last small person, then pivot was seen at index 2. Okay, so what do we do is we just add 1 to that index. We do 2 plus 1 and we swap the pivot with that guy. Okay. So if we see for this person, we have placed this person in the sorted position. Okay, now this person is in the sorted position in this entire array. In such type of implementation, what we can do is we can just eliminate, or in our partition we don't include the pivot anymore. We take out this guy, and now whatever we have left with is only this portion which needs to be sorted. Okay, let me do this also once again. I'll take this example. Now here what do we want to do? Our coordinators don't work in the same way as like left pointer or right pointer, but rather one guy is at standby and one person walks the queue. Okay, and this is our pivot. So this person walks no matter a person is of greater height or smaller height. Okay, let's see what happens. At this moment, somebody is of smaller height. Okay, fine. Um, so what I do is I ask this person, where did you see somebody of smaller height? This guy will tell me, okay, I don't know anything. I just saw somebody at -1. -1 means nobody existed. And I just add 1 to it and I get 0. So basically I don't have to do anything. I just update the counter. It becomes 0. Okay. Now I go again smaller height person. I don't have to do anything. Again the counter is updated. It becomes 1. And then I reach the pivot index. At this moment I don't do any comparison or anything. I just ask where did you see the last person who was of smaller height. Okay, this is where it is. And then what do? We add 1 to it and we swap with the pivot index. So in this case, um, if we plus 1, we will get the same pivot index's value and nothing will be swapped. And if we see, this person is already in the sorted position because everybody ahead of him is of shorter height. Now we remove the pivot and only 2 people are left. We do the same thing. We start and we see, do we see like somebody of greater height? Yes, we saw somebody of greater height. uh, Now what do we want to do? We don't update the counter at this moment, we just move ahead. Okay, as soon as we saw somebody of smaller height, we ask this person, where did you see the last known smaller person? This guy says, I don't know, -1. Okay, what do? We just add 1 to it and we swap the position of this current pivot index. Okay, so if we see now, this portion of array is in the sorted form. Same thing is for these two. We can quickly do that example also. The coordinator here. This guy keeps a note of where the last small person was seen. In the starting of the iteration, there is no information known, so we just initialize it by -1. Okay, whereas do we see somebody of smaller height? No, this guy moves. We don't update any counter. We reach the terminal condition. At the terminal condition, whatever value is here, we just add 1 to it because that is what the understanding is, that this is the position of last known small element or last seen small element. Okay, so we just add 1 to it and swap the pivot index with that. So even this portion of array is sorted. Now when we join everything back, the whole array is in the sorted position. So that is how the quicksort works. I'll be doing a quick implementation in JavaScript, and I will choose that first style or first variation where there were independent left pointer and right pointers. Let's begin by writing function quicksort. Let's accept an array and the low index and high index values. Then what is our terminal condition? Our terminal condition here is the low index should not be greater than or equal to high index. If it happens, then we return our array. Okay. Now, where do I want to start my left pointer from? I want to start it from the low index, and where I want to start my right pointer from. Right pointer I want to start from the high index -1. And what is my pivot index? Actually, for pivot index, I don't need a new variable. It's just for the sake of simplicity, I am creating a new variable over here so that it's clear while using it. Although it's always a high index, so we can actually leverage the high index value itself. I will also require a swap function. So let me just write the swap functionality separately. Okay. Now what do I want to do? I want to run till my left pointer is not equal to right till my right pointer is not equal to left pointer. I want to scan the arrays, and let's start from the right side. What do I expect towards right side? I expect elements to be of greater value than the value of pivot, and I also want to take care of the condition that left pointer and right pointer are not at the same position. Okay, like this is our terminal condition again for this loop. We want to stop if left pointer and right pointer are same, and we don't have to like cross these pointers at at this moment. Like we decrease our right pointer and move towards the starting of the queue or array, and towards the left hand side, what do I expect? I expect values to be of lesser value than what is there at my pivot index. And again, I have to be mindful of the same condition that both left pointer and right pointer are not same. And what do I do from here? I move one step towards the right pointer or towards the end of the queue. Once the anomalies have been found at the right side and the left side, then what do we want to do is we want to swap. And what are we doing over here is we are sending values which are greater towards the right hand side and values which are lesser towards the left hand side. Or we can say that smaller values go towards the starting of the queue, and bigger values or larger values go towards the end of the queue. Once this is done, I do one more comparison and I check wherever like we have stopped, whether I take it left pointer or right pointer, it does not matter because both the values are same at this moment. We just want to compare what's the value is greater than value at pivot, or like the value is greater than value at the pivot index or not. If yes, then we swap these two. And once this is done, I want to run quicksort on the uh, like left partition and the right partition of my array. Okay, so left partition starts from low index and goes till where I have stopped, like till left pointer. Okay, and now the right portion is starting from the left pointer plus 1 and till the high index. So in this particular implementation style, these like I am including the low index, I am including the element where exactly the partition has happened. Okay, whereas in the second style where we have the pointers at both the sides, in that case um, we can always have this condition as left pointer plus 1 and the other portion as left um, this as left pointer minus 1 and other as left pointer plus 1 in the other style of implementation. Okay, but in this particular style of implementation we would require to include whatever that partition value is in one pass. Okay, I'm not including in both. It's not like I have included value at left pointer in the second part also. Okay, so once this is done, the array should be sorted, and let's return from here. We can test it out quickly by passing some sample data. So we have 6 elements. That means 5 should be our high index. Okay. Let's test it out. 1 2 4 5 6 9. Okay, this looks sorted. So this is it for the quick sort. There are different variations of quick sort. We have randomized pivot where you can choose any random element as a pivot. It uh, and then based on certain type of data, choosing a particular style of selection of pivot also helps. And these implementations don't take care of the duplicates in the data. There is a separate implementation for handling duplicates, and there is the second type of implementation also that I have not shown here. We can do that in a separate video. That's all. Thank you for watching.